Hello everyone, welcome to the lecture series of Computer Organization and Advanced Microprocessors. This is our 11th lecture, and in this lecture we will learn about the flip-flops. Flip-flop is basically an example of sequential circuits. We have already studied about the combinational circuits and adders. That is the example of combinational circuits, and now we will see the example of sequential circuits, that is flip-flop. So let's start and understand the concept of flip-flop. Okay, so now see on the screen, we have an animated image of a flip-flop, that is the circuit. As you can see in the image that we have two NOR gates we have taken. Then we have two different inputs, that is one is a S and the second is a R, which stands for the set and the reset process. And we have two outputs, one is a Q and the other is the Q bar. Okay, so here Q is my main output and Q bar is the complemented output or inverted output, I can say. So what is happening over here, that this circuit contains two gates, right, and two different phases. It is just like on off. We can consider the example of our normal switch, which has a set and reset, means on off every time. So what happens when I'm saying that it's a set phase or a set status of the switch, it means the next phase always be the reset. Or if I'm saying the current state is on, it means the next phase definitely going to be the off state, right? So this is a simple switch type of concept, also we call it latch. So now let's understand that what is happening in the image. As you can see, green line, 1 is my set input, I got 1, but because it's a NOT, I got the 0. This 0 becomes the input for the next cycle. Again I got 0, but because it's a NOT, I got 1, and this one becomes the input for the next phase or a next state. And this way, this sequence continuously going on, then that's why we call it a sequential circuit, right? In a sequential circuit, what happens, every time you get some output and that output becomes the input for the next phase or a next state, we can say, right? So this is a basic concept of the flip-flop. Now let's see what is flip-flop and what are the different characteristics of a flip-flop. So flip-flop is an electronic circuit with two stable states that can be used to store binary data. Yeah, now we know, right, that what is flip-flop. So flip-flop is an electronic circuit that we know, and it has two stable states because it can be either in a on or a off mode or off state, we can say, and that can be used to store binary data. Yes, because flip-flop is an example, or a flip-flop is a type of sequential circuit, and in a sequential circuit what we do, whatever the output we get, that output becomes the input for the next phase or a next state. So to use that output in a next state, we need to store that output temporarily, and for we can say that a flip-flop can be used to store binary data. That data can be anything, either it can be a 0 or a 1, and always it stores only single bit at a time. We can store a single bit at a time in a flip-flop. So this is just a definition of a flip-flop. Then it's a bistable multivibrator. Bistable, why bistable? Because it has a two state, and multivibrator is a term which is used in a electronics field to tell or to define or to identify the type of circuit. So we can also say that flip-flop is a multivibrator type circuit. Then the third point says the stored data can be changed by applying varying inputs. Of course, if we take an example of our normal switch, then we know that it has only two states, on off, on off. So if the current state is on, then of course I need to apply some input, some force on the switch to change the state, right? The first it has an on state, and the second I'll get the off, and vice versa. So without applying any input, we cannot get any output, right? And whatever the input we are applying, that input will be stored in the device, in the circuit, until we give the another input, we apply the another input. Then we have a fourth point, that is flip-flops are fundamental building blocks of digital electronic system used in computers, communications and many other types of systems. Okay, fine. So if you want to design any circuit, if you want to design any electronic circuit for any digital electronics circuit, you need a flip-flop, because without flip-flop it is not possible to design a circuit. Flip-flop is a very basic building block for any digital electronic systems. And the last point says flip-flops are used as a data storage element. Yes, we have already discussed about this, that if you are working with the circuit, if you are working with the digital systems, and if you want to store the data somewhere, then you can use the flip-flop, because flip-flop can store your data. It can store either 1 or a 0. Now the question is how to trigger the flip-flop, right? Because to change the state we need some trigger. So basically, to trigger the flip-flop, or to alternate between the two states, we need to apply the current or a power supply. So when we apply the current to the system, it changes its state, right? So to maintain its state indefinitely until it receives an input pulse called a trigger, which forces it to alternate its state. Yes, we know that to trigger any flip-flop, to trigger the circuit, we need current or a power supply, and until we apply the next trigger to that circuit, it will not change the phase, or it will not change the state. So we can say that maintain its state indefinitely until it receives an input pulse called a trigger. So what is trigger? A trigger is nothing but a pulse or an input pulse we apply to the circuit to change its state, right? And the last point, once the circuit changes state, it remains in the state until other trigger is received. Of course, if your circuit is in an on state, so until you are not applying the force for the off, until that it will not change its state. Also we have already discussed this point, that the why we call it a flip-flop, because flip-flop comes from the circuit's nature. Of course, flip-flop nature of the flip-flop, as you can see in the image, animated image, bulb image, that when you apply the power supply, or when you apply the circuit positive or a zero voltage, any voltage you apply, it changes its state, on off like that, right? So it's nature of the circuit, and the state of a flip-flop is changed by changing the input signal. If you apply the on, you can see in the left side image, then the state of a flip-flop is changed by changing the input signal. How you are changing the input signal? Based on that, it changes its output, and this change is called a trigger. And the transition, because transition we can say, right, transition, it causes it say to trigger the flip-flop. Now let's talk about the different types of flip-flop. So there are total 4 types of flip-flops. First, SR flip-flop, second JK, third is a D, and the fourth is a T flip-flop. So SR is a basic type of flip-flop, and all the other like JK, D and T all are the advanced version or a updated version of the SR flip-flop. So first we'll start with the SR flip-flop, and then we'll see about the all the other 3 flip-flops. Okay, now let's start with the SR flip-flop. As you can see on the screen, that we have 2 different logic diagrams. Both are same. Keep in mind, both are same flip-flop, same basic building block, but the difference is, if it is asked for the SR, go for this. This is my SR. This is SR flip-flop, and if it is asked RS, then go for This diagram, this is RS. Why? What is the difference? In SR flip-flop, as you can see here, it is used NAND gate used, and in the RS flip-flop, NOR gate has been used. So, and the trigger, the output, everything is same, only the difference is the position of the set and reset options, right? So this is the only difference between these two things. So keep in mind that if it is asked for the SR, go with the NAND gate and set and reset option, set first and then reset. But if it is RS, then go for the NOR gates and first R and then set. So now let's understand what is SR flip-flop. So we'll talk in the context of RS flip-flop, that is this diagram. We'll talk in this context. So okay, let's start. So basically a RS flip-flop is the simplest possible memory element, we can say, because if you want to design any circuit, we know that we require flip-flop, because flip-flop is a basic building block for any digital circuit, and RS flip-flop is the simplest possible memory element, and it is constructed by feeding the outputs of the two NOR gates. Rest we can see two NOR gates back to the other NOR gates input. See, because we have taken two NOR gates, and what we are doing ultimately, we are applying the output of those NOR gates again to the NOR gates, right? And the inputs R and S are referred to as the reset and set inputs respectively. To understand the operation of the RS flip-flop, we will consider this logic diagram. We will consider this logic diagram. So, and simultaneously we will understand the truth table of this SR flip-flop. You can see there are 4 columns: S, R, Q of t plus 1 and state. So now let's understand. So if I have S is equal to 1 and R is equal to 0, means we are talking about this state, we are talking about this phase. If I have S is equal to 1 and R is equal to 0, the output of the bottom NOR gate is equal to the 0. Of course, right? If you remember our first animated image of the flip-flop, we know that when you apply the 1 and 0, then we have, this is NOR gate we have, and what will I get in the Q dash? Equal to the 0, right? And hence both inputs to the top NOR gate. This is my bottom NOR gate and this is my top NOR gate. So both inputs to the top NOR gates are equal to 1. Yes, right? And thus my Q is equal to 1. The Q will be the 1, and therefore we can say the input combination S is equal to 1 and R is equal to 0. Means we are talking about this line. Yes. So S is equal to 1 and R is equal to 0 leads to the flip-flop being set to Q is equal to 1. So this is my actually a main output and this is my inverted output. So what we are going to store, we'll always store this output because this is my main output Q, because Q bar is my inverted output. So what will I get? I'll get my final output Q is equal to 1. Now let's consider the second state, that is S is equal to 0 and R is equal to 1, means this point, this third row we are considering. So similar to the arguments we have already discussed in the above statement, the outputs become Q is equal to 0 and Q dash is equal to 1. That we can say that the flip-flop is reset, right? If this point is my on, then we can say that this is again I'm off and again I'm resetting my output. So my state will be the reset state. What happens if my both the inputs are 0? What will happen if S and R both are 0? Just assume that a flip-flop is a set, right? And then the output of the top NOR gate remains at Q is equal to 1 and the bottom NOR gate stays Q dash is equal to 0. Let's assume that. And similarly, when the flip-flop is in a reset state, is it really possible? It will remain there with this input combination, right? Because therefore with input 0, S0 and R0, the flip-flop remains in its state only, because it is not going to change any state. Whatever the state it is, it will remain in the same state, right? In the last combination, that is my 1 1. So what if I have s is equal to 1 and r is equal to 1? So this input combination must be avoided. Keep in mind, because this input will produce the same value at the two outputs, that is q and q dash, which is not possible, right? It is never possible. It is not possible at all that you get q and q bar always same, because q is original output, main output, and q bar is an inverted. So you will never get two same outputs, and so the last combination, that is 1 1, is not possible, or we can say that it is invalid. So this is just a basic idea about the SR flip-flop. So just keep in mind that SR and RS both are same, just the difference is which gates you are using. Ultimately you will get the same output in both the gates, both the circuits. Okay, so if we sum up all the discussion about the SR flip-flop, then here we have total 4 points. And the block diagram of the SR flip-flop. You can see in the block diagram, now we know, right, what is block diagram. So block diagram, you can see the two inputs, that is S and R. Clock is my enabled line or the power supply or input pulse, and Q and Q bar both are my outputs. So let's sum up all the points. So first, the set reset flip-flop is designed with the help of two NOR gates and also two NAND gates. Whatever the asked, if it is SR, then go for the NAND gates, and if it's RS, then go for the NOR gates, right? The design of such a flip-flop includes two inputs called set and reset. Now we know S means set and R means reset. There are also two outputs, Q and Q dash. Yes, Q is my main output and Q dash is my inverted output or a complemented output. And the flip-flop has mainly 4 states. You may be thinking that till the time you are saying that the flip-flop has a 2 state, and now you are saying that 4 states. 4 states because two main states, that is my set and reset, but also we have seen that what if I apply 0 0 and 1 1 to my inputs. So also I'm getting two different states, that is the whole state and the avoided states or the invalid states. So we can say that 4 different states. So it was all about the SR flip-flop. Now let's talk about the JK flip-flop. So as you can see on the screen that we have a logic diagram for the JK flip-flop. If you see the diagram carefully, you can see this. You can see that this portion is nothing but your SR flip-flop. Remember the SR flip-flop where you have two NAND gates, or it can be a two NOR gates, and the output of the one gate will becomes the input for the other gate. So this is my basic structure of the SR flip-flop. So here we can say that JK flip-flop is an extension of SR flip-flop, we can say, or higher version of the SR flip-flop. Similar way, we can see the another diagram. See this. This is using this portion. See this. Right. This is my RS flip-flop using the NOR gates. So now let's understand that what is actually happening with the JK flip-flop. So just see on the screen. See what is happening. We'll take the example of this SR flip-flop. See this. When you are talking about the SR flip-flop, then see this portion, this output. This output is going to be the input for the lower AND gate, and the output of the lower will be the input for the upper gate. So this thing happens in the JK flip-flop. You have SR flip-flop, and every time whatever the output you get in the SR flip-flop becomes the inputs for the J and K inputs, but in the reverse order, like top output goes to the down and down or a bottom output goes to the upper gate. So this is how JK flip-flop works. Now let's see how what are the different states we get for the JK flip-flop when we change the inputs. So here we have truth table, and you can see that we have different columns. This clock column is nothing but the trigger, right, for the flip-flop. So it will trigger my flip-flop. Now let's focus on the values of J and K. That is my J and K, and why Q and Q dash are most important here to check the state, because we know that this Q is always going to be the input for K and this Q dash is going to be the input with the J. So these are the in a combination. So it is very important to see what is the Q dash, what is Q and what is Q dash. Now let's see that let's start with the first option, that is my 0 0. What if my J and K both are 0? Here you need to understand this thing, that the outputs of AND gate, as you can see in the figure, will be the low. Of course, because I have both the values 0, in that case every time I'll get the 0, and 0 means see this 0, wait guys, okay, so 0 means low and 1 means high, right? 0 means there is no voltage, and if there is no voltage, there is no change in the state, because it is solely depends on the values of the 1. If you have a 1 in your input with any combination, then there are chances to change the output, otherwise it will remain the same, right? Okay, so it means that if I have this 0 and 0, so of course my Q will remain the Q and Q dash remain the Q dash only. So there is no change in the state, whatever the state it is, there is no any change, because everything will remain the same, because we are applying the low voltage or a no voltage, right? Okay, now the second combination, this 0 and 1. Okay, so what happens when you say that my J is a 0 and the K is equal to 1? In that case, the output of the upper AND gate, means we are talking about this upper AND gate or an AND gate. Upper AND gate is suppose low, because 0 is low, right? So when we are saying that we are supplying the J, so this is my 0. 0 is going, okay, and then so of course because it is 0, so it is low output, it will give the low output, and therefore it is not possible to set the flip-flop. Obviously, because we have a low voltage, so how can you set the flip-flop? And because as here K is equal to 1, so the output of the lower AND gate, that is my this lower AND gate, or I can say the R, will be the high. Of course it will be the high, because I am supplying the 1. So in that case I need to check what I need to check. I need to check the output of this what is the output of this, because it is solely depends on this. So I can say that the value of the K and the value of the Q matters to change the state of the device when my K is 1 and J is 0. Fine. So this is about the second combination. Now let's see this combination. What happens when you have a 1 and 0? And yes, in the previous section, like 0 and 1, so of course it will reset the value, right? Because ultimately if I have a Q, because I have a Q0 and a Q dash is a 1, so it is resets Q to 0. Simple, right? Now what happens when when we give the input 1 and 0, like my upper gate will have a 1 value and the lower gate will have a 0 value. So what will happen in that case? So the output of the lower AND gate is suppose low. In this case we can say that lower, this is my 0, that is my K. So it is 0, and because it is a 0, it gives the low output, right? Low output, and therefore again it is not possible to reset the flip-flop. In the uppercase, setting is not possible, and in the lower, reset is not possible, because we have a 0 for the in the uppercase j is a 0, in the lowercase k is a 0, so it is not possible. And the output of the AND gate or the set will be the high, of course, because this is 1, right? So my this input will be the upper gate will give the 1, and so I'll get the high output, right? And so we can set the flip flop. And the last option, that is this portion, this one, last portion. So what happens when you have both the values 1 1? So in that case, the flip flop can be set or reset depending upon the previous state of the output. So this case we call it a toggle case. Here the best example for the toggle case, if you have seen the switches, like if you have a staircase and your staircase, and we have many times we have seen that normally we keep two switches, one when we start the staircase and at the end of the staircase, so we can toggle the switches, right? So it is always dependent on the previous output, right? That what was the previous output of the other switch. So this case we call it a toggle case. So guys, this is about the JK flip-flop. Please read, listen this video again and again and again, and also search for the different refer other videos and other materials as well. And one thing, make sure that when you draw this truth table for the JK flip-flop, make sure that you have entered all the possible values and you have checked with the AND gates, you have checked with the NAND gates, that what will happen when you enter these values. So please check each and every value, just like our first animated image where we have already shown that what happens when you give the 1, what will be the output, and how that output will be the input, and then again what will be the output. So please go and check. Now let's see the block diagram of the JK flip-flop. One thing we need to know, that JK stands for Jack Kirby. It's a name of the inventor, and J means a set and K means a reset. It is similar to the SR flip-flop, means whenever you see the J means we are setting the flip-flop, and whenever you see K means we are resetting the device, right? And as you know, that block diagram means how what is the outer look of your device. So two inputs we have and two outputs we have along with the clock pulses. So here we have total 3 inputs, and why we have shown the T, because this T is nothing but the remember the output of the SR flip-flop. So here we have mentioned the T. Okay, so as you know, that the JK flip-flop basically is an RS flip-flop, right? With its output Q dash and Q, and AND together, like A and D ANDed together with J and K respectively. Now we know this. And this type of JK flip-flop normally has no special name, because we call it JK, and we understand that J is a set and K is an R. And one thing we need to note down here, that the connection between the outputs and the inputs to the AND gates determines the input conditions to the R and S, when especially we have J, K and both are 1. J, K both are 1. So here you need to understand, please keep in mind that the connection between the outputs and the inputs to the AND gates determines the input conditions to R and S when J is equal to K is equal to 1. When we have J and K both are 1, at that time we need to check this. Fine. Okay, so this normally this connection is nothing but the causes the toggling things, and because we are toggling the device or inputs or outputs, it eliminates the invalid condition, because it is never possible that both will remain in the both will be the invalid states. So here this is the main advantage of the JK flip-flop, that because we can toggle the device, because we have used SR flip-flop along with the JK inputs, we can toggle the device, toggle the outputs, toggle the inputs, so there is no chances of the invalid state of the device. And so this is most commonly used device or a most commonly used circuit, right? Okay, so it is all about the JK flip-flop. Please watch other videos, other reference materials, and please watch it again and again. Okay, now let's talk about the D flip-flop. What is the meaning of D flip-flop and how does it work? So as you can see on the screen that there is a now you can easily identify, right, this diagram. See this portion, this portion. So this is nothing but my RS flip-flop, right? Remember? And this is nothing but the JK flip-flop. So we can say that, and after adding this gate, we got the D flip-flop, right? So here we can say that D flip-flop is an extension of JK and JK is an extension of the SR flip-flop, right? See, either you say it's a JK flip-flop or a KJ, or you can say that RS flip-flop or SR flip-flop. There is no change. There is only change is in the gates you are using. So don't get confused between this. Ultimately, D comes from the JK and JK comes from the SR, we can say, or extension of the gates, or the advanced version of the existing circuit, we can say that, right? Okay, so now let's understand that what is happening with the D flip-flop. And as you can see that there is only one change. If you notice, there is only one change. See, enable inputs we have, right? Enable is there, but what is the difference? That I have added one more input, that is D, and what I am doing, somewhere I am inserting the original D, and here the inverted input. Means if 1 is there, in that case 0 will be here, right? And if I say 0 is here, in that case it will take the 1 over here. And again, because we know that all are dependent on each other, so ultimately finally it will be totally dependent on this values as well. So what matters over here is my Q value and my D value, that what I am passing, like 0 and 1 or a 1 and 0, whatever the value it is, right? So this we will understand from the truth table. So here we have the truth table for the D flip-flop. As you can see, now we know that what is clock pulse and all, right? So this is my clock pulse. Okay, this is my clock pulses, and 0 means low, 0 means low, and 1 means high, right? Okay, now as I told you that in this flip-flop, my outputs or the state of the device solely dependent on the two things, that is D and Q, because we know that whatever the Q is, Q bar always will be the inverted, right, or a complemented output. So we need to understand, we need to know what will be the D and the Q, because here passing only one input. So because D has only two possibilities, right, 0 and 1, in which case when my clock pulse is 1 or high, because when it is a 0 there is no change. We know whenever you have a low voltage or the low voltage or the low input, there is no change in the state of the device. But when it is one, then and only then it is possible to change the state of the device. So this is one. So in that case, because I have only one input, see this, because I have only one input, so as because two bits of two possibility, that is my 0 and 1, and the same case with the q. So if the 0, both the values are 0 0, in that case I can reset q to 0, and if both are 1, we can set q to 0. This thing you can check by doing the same thing like the first animated image, right? Just check that what happens when you insert the 1, when you change the 0, because every time, see, every time you have to check the status, like what you are inserting over here, what you will get here, what you will get here, what you will get here, and what you will get here. And at the end, because everything is going to be the what all the outputs is going to be the input for the next cycle, so you have to take care of all these things, right? So this is the simple idea of the D flip flop. Now let's see the block diagram of the D flip-flop. It's easy, of course, right? It is similar, like because we have only two possible inputs, that is my D and D dash, because one is a normal input and the second is inverted input, because we had used the NOT gate over there, right? And I will get always two outputs, that is Q and the Q bar, along with the clock signals or the clock enabled signals. Fine. Okay, now let's see what is the meaning of the D flip-flop. So the meaning, or a D means the delay or the data. Sometimes you can find D for the delay and sometimes you can find the D for the data. So is the input state for the D flip-flop. Either you are using the D flip-flop to delay the signals or to delay the process, or sometimes you are directly providing the data to the device. So based on what type of device it is, we call it a delay or the data. And the Q and the Q dash represents the output state of the flip-flop. Yes, we know any flip-flop you are using, ultimately Q and Q bar will show the status, because the state of the device is solely dependent on the values of the Q and the Q bar. And based on the inputs, the output changes its states. Yes, we know whatever the outputs will get, and it will change my next output, right? Because that output is going to be the input for the next phase. And but the important thing to consider is all this can occur only in the presence of the clock signal. Yes, it is very important thing to understand. Everything is possible only you have clock pulse or a clock signal. Means you can say that your input is enable, right? Enable means you are providing the power, you are providing the input signals, or you are triggering the flip-flop, right? So it is all about the D flip-flop. Okay, now this is the last flip-flop, that is the T flip-flop. Now let's see what is T flip-flop. See, you can see in the diagram again the same thing, that see this. What is this? Now we know what is this. This is my SR flip-flop. This is my JK flip-flop, right? And here what I am doing, along with the J and K, because I know that this is my J and this is my K, so along with the J and K inputs, I am providing one more input over here. See, this is my T input, right, along with the clock pulse. So, and it is not the inverted thing, like just like the D flip flop. It is the directly we are providing the value, that is my true value, and this will change. This will totally dependent on the my clock pulses, because whatever the input I am giving to these gates, it is dependent on the output and also with the clock pulse. Now you have to keep in mind that clock pulse is very important part or a very important factor for any circuit, because it is because you can know circuit is a circuit state of the circuit is dependent on the clock pulse and as well as on the outputs, right? So this is about the T flip-flop, logic diagram of the T flip-flop. Now let's see the truth table. It is very simple truth table, because ultimately what we are doing, we are only providing one input at a time, and that input can be the 0 and it can be 1. So based on the value of the T, I will change the status of the Q and the Q bar, right? This you can verify by, and again the same thing, this thing you can verify by writing, by checking all the inputs, and how, like suppose you are giving 1 over here, then what will be the output over here, then what will be the output over here, and what will be the output, and then this input, this output will be the input for this. So this thing you can cross check by providing the data, right? So this is a simple flip-flop, that is the T flip-flop, and normally it is used for the toggling the switch. One thing very important about the T flip-flop is it is a self-toggling device, right? You don't need anything, you need only enable clock pulse. It will automatically toggle itself. So this is the most important main benefit of the T flip-flop. Now let's see the block diagram of the T flip-flop. As you can see that now we know, right, that T flip-flop takes only one input and the clock pulse, and we get always two outputs. It's very simple flip-flop T. It's a self-toggling because and it is solely depends on the clock pulse provided, right? Okay, so now let's see what is the actual meaning of the T flip-flop. So the T flip-flop is, in a T flip-flop, T stands for the toggle. We know, right, the meaning of the toggle, right? When you have a 1, it automatically change the state to the 1 0, and if it's a 0, then it automatically changes to the 1. So it is a toggle case. So flip-flop changes its output on each clock age. Every time it gets the clock pulse, and every time it will change the status, right? If it's 1, then 0. If it's 0, then 1. So it is a self-toggling device based on the clock ages or the clock pulses. What the clock pulses it is getting, it is based on that only. So it is based on based on that it will give the output, right? So it is a very simple, and it can be made from the JK flip-flop, as we know that T is again the extension of the JK, and JK comes from the SR, right? So it is all about the T flip-flop. It is most easiest flip-flop. Okay guys, so it was all about the flip-flop. Please refer some more videos, refer more materials about the flip-flop, and whenever you check the truth table for any flip-flop, make sure that you have drawn this device and you have checked each and every input and its output, so you can get so you can know that how the device changes its state, right? So happy learning, keep learning. Thank you.